Hello and welcome to our senior design presentation. Today we are going to present our project PLATICA, which stands for Personalized Language Acquisition Training and Instruction Chatbot Assistant, which is a chat and grammar AI. The reason for this acronym is that PLATICA in Spanish means to chat. My name is Andres.
My name is Nan.
My name is Philip.
And I'm Evan.
And our advisor is Dr. Fang. First, I'll go over a quick agenda for our presentation. We'll introduce our problem statement, discuss related work versus our contribution, examine the requirements and constraints of our project, then explain the use cases and design rationale, give details on the chatbot and the grammar checking functionality, and conclude with a demo and lessons learned. English is immensely important and useful in our society. However, in our area, there are many people who are learning English as a second language and have limited options to practice speaking English with native speakers in a way that is casual and emulates regular conversation. We aim to solve this issue with our project PLATICA, a low-cost mobile application that anyone can use to build experience conversing in English. PLATICA takes advantage of state-of-the-art deep learning techniques like recurrent neural networks to provide a conversational chatbot experience that can simultaneously provide a realistic experience along with real-time grammar feedback to the user so they can enhance their English learning. Now I'll discuss some related work to this project. There are many existing chatbots that usually focus on specific areas, such as goal-oriented chatbots or dialogue-based ones. Xiaoice is a very popular chatbot in China, which focuses on human emotion and communicating empathetically with users and consoling them through difficult circumstances. Mitsuku is another chatbot that held the record for the best conversational chatbot before being beaten by Google Mina and then Facebook's newest chatbot, Blender. Blender was released last month as open source and was trained on 1.5 billion conversations with almost 10 billion parameters. As for language development and grammar feedback, there are also various products related to this. Duolingo is probably the most popular language learning app, but it focuses mostly on memorization of words and phrases instead of having natural conversations. Grammarly is a popular Google Chrome extension that can highlight users' grammar mistakes in emails and give alternatives on the screen. Our contribution to this field is combining both a conversational chatbot and a grammar correction system in an attempt to provide natural conversation with helpful feedback. Our method of noise insertion in combination with deep learning in English is a novel component. We do this through a simple-to-use mobile app that can be chatted with live and that provides a history of users' mistakes and progression. PLATICA as an end-to-end learning pipeline could also be adapted to other languages in the future. We split the requirements for this project into functional and non-functional requirements. For functional requirements, the most important requirements were the functional conversational chatbot, which would have to be able to maintain a stimulating conversation, as well as a working grammar correction system. Other functional requirements were the compatibility of the mobile application to be able to run on both iOS and Android. Lastly, we wanted to make sure that the app would be able to be used hands-free so that a user could use it during a commute. Now for non-functional requirements. The app would have to be easy to navigate, especially for a user who is learning English. The chatbot would have to provide a friendly, encouraging, and respectful conversation in order to maintain the user's attention and interest. Grammar corrections would need to be made quickly and in an understandable format. For security, users' credentials and conversations would need to be kept private and secure. We used a few different technologies for this project. For the front end, we used React Native with the app written in JSX, HTML, and CSS. For the backend, we used the Python microweb framework, Flask, deployed on Amazon AWS EC2 instance, with the chatbot and grammar checkers written in Python using the Keras deep learning library, and a tool which provided neural machine translation models called NMT Keras. Now I'll pass it on to Evan, who will talk about the design of the project.
Thank you, Andres. The PLATICA user will have a small set of simple yet robust actions they can perform on our app. The user will be able to first register, log in, chat, receive chat responses from our PLATICA chatbot, and view their updated progress and analytics. This activity diagram gives a brief overview of the actions the user may perform within our app. Once the user signs in, they will have the choice to either chat with PLATICA or view their progress. If they choose the latter, they will be able to see both visual and numerical representations of their progress. If they choose to chat with PLATICA, they will be able to send messages and receive responses through a chatting interface. If they want to stop chatting at any time, they may go back to the original landing page where they can view their updated progress, toggle settings, or log out. We decided to implement a simple pipelined architecture. The user will start by interacting with the client application. As the user speaks to our chatbot, their data is sent to our system, where speech-to-text technology converts the audio to readable text. The data is then fed into our grammar and chatbot models. The grammar corrections and chat responses are then relayed back to the user via text-to-speech capabilities, as well as displayed on the UI. We had a variety of technologies to choose from when developing our initial design. Our final choices came down to those which we are most familiar with and which provided us the greatest variety of use cases. For our front-end development, we chose React Native, a mobile application framework providing cross-platform app development. React Native provides optimal performance, allowing us to build a smooth native experience for the user. Furthermore, having a mobile application allows users to use PLATICA on the go. For our backend, we built a REST API with Flask. Flask is a microweb framework written in Python. This was an easy choice for us, since we all had experience programming with Python, and the language's simplicity allowed us to easily implement robust backend logic when handling routing requests. Furthermore, this allowed us to easily integrate our Python deep learning models into the backend. Lastly, we chose to build our chatbot and grammar models in Keras, a neural network library written in Python. Keras abstracts backend TensorFlow operations, allowing us to create powerful deep learning models in Python. Our application backend itself is hosted on an AWS EC2 instance. EC2 provides a fast Linux-based computing environment perfect for running our models on the cloud. Our React Native front end communicates with the backend REST API by relaying JSON payloads via GET and POST calls. The user's microphone audio is converted to textual data via API calls to a Google Cloud speech-to-text instance. Text responses from the chatbot are then converted to audio via an API from our SDK. Both chatbot responses and grammar corrections are simultaneously displayed on the UI. For our deep learning models, we had access to 2 NVIDIA GPU servers. The first server, DeepInfo, utilized 4 GTX Titan X graphics cards, each with 16 gigabytes of graphics memory. The use session for this GPU was unlimited, allowing our models to train without intervention for days on end. The second server, Wave, utilized 2 Tesla V100 graphics cards, each with 32 gigabytes of graphics memory. Each use session on this server, however, was limited to 48 hours. I will now hand it off to Philip so he can discuss neural machine translation.
Thanks, Evan. So now I'll talk about some of the deep learning technologies that we actually use to develop our conversational chatbot and real-time grammar checking system. The models we use for these systems are neural machine translation models. We use a library called NMT Keras, which is built on top of Keras to build and train our models. Here's a diagram of the architecture of a neural machine translation model using an attention mechanism. This one is a variation of a sequence-to-sequence model. To give some brief background information about sequence-to-sequence models, they were first introduced by Google in 2014 to provide a model that can predict a sequence of data given an input sequence of data, hence the name sequence-to-sequence model. These models proved to be very useful for a multitude of applications, including language translation, speech recognition, and video captioning. Regarding the architecture of a sequence-to-sequence model, at a very high level, it consists of an encoder and decoder. The encoder is built from many recurrent neural networks that are trained to find patterns in input sequences. After reading an entire input sequence, the encoder produces a vector that encapsulates the semantic meaning of the sentence. This vector is then fed as the initial state to the decoder, which is used to predict the first word of the output. This in turn produces a new hidden state, which is then used to predict the second word. And so this process repeats until the model predicts that the end of the sentence has been reached. And so as it turns out, this model can be used for training both the chatbot and grammar checker. For the grammar checker, the input is a grammatically incorrect sentence, and the output is a correct sentence. It automatically learns the grammar rules of the English language without us having to write any of the rules by hand. And then secondly, for the chatbot, the input is a sentence of context in the conversation, while the output is the response that was actually said to the statement. And so our models are trained on these input-output pairs. So we ran many different experiments for our chatbot. Firstly, we experimented with the model architecture, including an LSTM-based versus a transformer-based sequence-to-sequence model, the former of which was introduced in 2014, while transformers were developed more recently in 2017. We also tested with different data sets. The Open Subtitles dataset consists of over 13 gigabytes of movie subtitle data. Although there is a lot, the quality is generally regarded as inferior compared to other datasets. Secondly, we tested the Persona Chat dataset, which is a dialogue dataset of 162,000 utterances between crowd workers who are instructed to portray a given persona. This is a much higher quality dataset of conversations between two individuals getting to know each other. And then lastly, we tested the empathy dialogue dataset, which consists of 60,000 utterances between individuals having one-on-one conversations. These conversations specifically involve empathetic responses. Next, we tested various model parameters. These are some of the key hyperparameters that define how well our model can fit our data and how our model produces outputs from what it learned. They include the number of encoding decoding layers, the hidden size, beam size, learning rate, and batch size. We also experimented with the amount of context taken into account to predict the next response, from having up to 3 utterances to only 1. And then lastly, we used the perplexity metric to evaluate our chatbot, which was originally proposed by Google Mina to automatically evaluate the chatbot specificity and sensibility. So now I'll discuss our findings from our chatbot experiment. In total, we trained and evaluated 20 different models, each taking about 2 to 3 days to train in total. We used TensorBoard to analyze the training and validation complexity to track how well the model trained. Based on whether it seemed to overfit or underfit, we then adjusted our parameters. So again, regarding the architecture of our model, we found actually that the LSTM sequence-to-sequence model provided the best results. We believe this is in part because of our limited data set, as transformers have been shown to perform better on extremely large data sets. Next, the data set that we found to yield the best performance was a combination of both persona chat and empathetic dialogues. These allowed the chatbot to respond with a particular persona and answer detailed personal questions. In addition, the chatbot was also able to respond with empathy. For example, to comments like "I was promoted" or "I'm exhausted," it will give sensible responses like "I'm great" or "I'm sorry to hear that." Moving on, through our method of testing mentioned, we found these parameters to yield a chatbot whose answers both made the most sense and achieved the greatest amount of diversity in its responses. An evaluation of the chatbot's responses was done using both the perplexity metric and manually interacting with the chatbot. As for context, we found that incorporating more context actually significantly increases the perplexity error, resulting in overly generic and nonsensical responses. So we limited the context to only the previous statement. Next, for diversity promoting functions, we tested also with functions that help the chatbot be more diverse in its responses. However, we found that responses were often grammatically incorrect, and so we left that out as well. And then lastly, for the perplexity metric, we found the perplexity metric to only be a rough guideline for the chatbot's performance during training. The perplexity of the model used in practice in our application is around 5 billion. And we determined this to be the best model through manually testing different types of statements, such as personal questions, knowledge-based questions, statements to evoke empathetic responses, and greetings and salutations. And although we achieved a perplexity as low as 168 in our experiments, this model actually did not prove to be the most specific and sensible of those tested. And lastly, just for reference, Google Mina achieved a perplexity error of 10. So here we provide a couple of conversation examples. On the left, it can be seen that our model was good at answering personal questions, such as "How old are you?" "What do you do for a living?" and "What do you do for fun?" In addition, it is also able to display empathy. For the comment, "I'm so tired today," it was able to ask what happened. When the user responds, "I did not get enough sleep," it responds sensibly with "I'm sorry." On the right, however, it can be seen that the chatbot has some shortcomings. For example, it has a strong tendency to rely on overly generic responses, such as "What do you do for a living?" and sometimes its answers don't make sense at all. So now I'll hand it off to Nam to talk about the grammar checker.
Thank you very much, Philip. So now I will talk about the grammar checker. The grammar checker is trained on a large data set of famous novels and grammatically correct conversation. It uses the sequence-to-sequence model with attention mechanism. The novels chosen are English classics such as Wuthering Heights, Jane Eyre, The Scarlet Letter, etc. And for the conversations, we put together these short conversations from the Tatoba project. So creating the data set for grammar checker, we did that by stochastically adding various types of noise to well-written and grammatically correct text. So here, noise refers to grammatical errors. Once we do that, we have two sets of text, one with noise and one without noise. A neural machine translation is trained to correct the set with noise using the clean set as ground truth. So here, each of the following common ESL errors has a 30% chance of being added to a sample. And then we have here a list of some common mistakes that English learners tend to make. I would like to discuss next the complete deep learning grammar checker pipeline in our application. First, we have the ground truth, which is the original data, correct English for sure. And we feed this ground truth into the stochastic error generator, which create some variants of one original correct sentence. For example, here we have the company owes its success to her. So that's the one original correct sentence from the data set. Then it would create 3 new sentences, the variants of the original one. Sometimes the variant contains no errors, sometimes the variant contains multiple errors. So what happens is the error generator gives us noise data, which is a mixture of correct and incorrect English. This noise data is used as model input for the LSTM sequence-to-sequence model at the bottom. This model at the bottom transforms the incorrect English to the correct English. So basically doing the task of grammar correction so to get to the ground truth at the end. So here are some insights that we found out when creating the data set for the grammar checker. Duplication is used to ensure a balanced mixture of correct and incorrect English sentences. This teaches the model to only correct wrong sentences and to let pass sentences that are already correct. Duplicating each sample means that the model is able to see different possible mistakes with any given sentence structure. And right here we have some information on the training set and the validation set. The training set has 1.5 million samples and about 50,000 words in the vocabulary. The validation set has about 270,000 samples and about 30,000 words in the vocabulary size. To evaluate the grammar checker, we relied on a wide variety of metrics, but the most important metric here is the Blue 4 score, which we use not only for validation, but also for training when to stop the model. Based on these metrics, we found out that the LSTM 256 model performed best, getting the highest scores across all these metrics. The leftmost column here, so 256, refers to the hidden layer size of the model. So now I'll hand it over to Philip to discuss the challenges.
Thank you, Nam. So yeah, I'll discuss some of the main challenges that we faced in our project. Specific for the chatbot, a significant challenge was generating unique and specific responses. However, this is actually a very common problem even in modern research. Just to put this in perspective, Google Mina, which is trained on 341 gigabytes of text compared to our data set of 14 megabytes, it still has these similar issues. Lastly, for the chatbot, as mentioned, the perplexity metric was inconsistent, and so evaluating our model could be tedious and time-consuming. As for the grammar checker, the model was highly dependent on the kinds of noise generated in the training data, and additionally, we weren't able to generate all types of noise in the training data. Lastly, for both Even using top-of-the-line GPUs and a significantly smaller data set compared to modern research in this field, each model took 2 to 3 days to train. This made it very difficult and time-consuming to find the ideal parameters and configurations for our models. Lastly, regarding deployment, it took a lot of communication with the creator of NMT Keras, Alvaro Peris, to deploy our GPU-trained models to our AWS Linux backend, as the library was primarily intended for research purposes only and for GPU-compatible machines. And throughout our project, we worked continuously with Alvaro to help develop the NMT Keras library. Then here, I'll quickly discuss our testing procedures for the various components of our application. For the backend, we tested this first with direct API calls from Postman. For the front end, we used local development using Expo. For integration tests, we did manual integration tests using mobile client and the Flask server. And for chatbot grammar checking, as already mentioned, we automated these using the perplexity metric and blue metric or manually testing this. So now we'll move on to our first demo, and that is the demo application, demo of the application. So here our user is going to register for a new account. And for security purposes, we're not showing the password. So now the user has the option to either chat or view their progress. So here our user is going to begin a conversation with PLATICA. So as we can see, our first grammar mistake is given as input, and our system is able to correctly correct the grammar and give a sensible response. So we can see even to specific questions, our chatbot can give sensible responses and also give grammar feedback. So here we can see even with multiple different types of grammar mistakes, such as subject-verb agreement errors, extra articles, and plural nouns, even with multiple grammar mistakes, we can get a correct grammar correction, which is very helpful for the user. So now for the sake of time, we'll speed up the speed a little bit. And even with more complex responses from the user, our chatbot is still able to respond sensibly. Okay, so here we've ended the conversation for now. And then now the user can either toggle the speech and then also view progress. And in progress, they can view the number of messages they've sent, the average words per message, any streaks, the correct grammatical rate, and the rates for the last few days, weeks, and months. And so that's it for our application demo. And now we will demonstrate the hands-free functionality of our application. And the volume is unfortunately a little bit low, so it would probably help to turn up the volume. That would help hear the chatbot.
Good morning.
Hello, how are you?
Good. How are you?
I am great, thanks for asking.
What do you do?
I work as a nurse.
I work at a stores.
Did you mean I work at a store?
Does you have a hobby?
Did you mean, do you have a hobby? Yes, I do. How about you?
I like swim.
Did you mean, I like swimming? I like to play video games.
For the sake of time, we're going to end our hands-free demo there, and I'll pass it off to Nam to talk about future work.
Thank you, Philip. So for the future work, we plan to publish the application on iOS and Android. We'll probably implement a multiplayer mode to make things more interesting. We can, as always, we can refine both the chatbot and the grammar checker to be able to generalize even better by considering other advanced approaches such as BERT and ensemble. Last but not least, we also plan to apply the same methodology on other languages to serve more learners. And that concludes our presentation on PLATICA. We can now take any questions. Thank you very much for your attention.